its development through innovation. So you might have heard of fusion. It's actually why we're all alive, because it's the power source of stars. So as our own sun works by fusing hydrogen in the middle of the sun. Why would we consider, I take this thing off, why would we consider fusion on Earth? Because it's the ultimate energy source. Right, so why do we go for this on Earth? It's easy. No polluting emissions, no carbon. The fuel is everywhere and inexhaustible. You can generate the power anywhere and at any time. Meltdowns are impossible. There's no long-lived waste products. Basically, you can supply energy to civilization for the entire history of mankind based on fusion. This is why stars run for billions of years. Just as an example of this, you take an oil tanker, you take the water that's displaced by it, you filter out 1/6,000th of the hydrogen, which is in the water that was displaced by it. You fuse it like what happens in the sun. That produces as much energy as in the tanker of oil. And it doesn't emit a single carbon atom from it. This has been known for a long time, since we figured out how stars worked. What hasn't been there is a plan to actually get to how can we harness this for humanity. And that's what's changed, and that's the theme of this discussion. So what is now in front of us is an idea, and this is the plan that we have effectively cooked up here at MIT, and I'll get about how we're going to get there, is the idea is that there's this little thing called climate change, and the need for expanding energy use, not just in the developed world, but all over the world to lift people out of poverty. And the problem is we supply an enormous fraction of this now with fossil fuels. What does it look like, even if we keep expanding all the present non-carbon energy sources, is like what can there be that actually fills in that wedge between now and the middle of the century, which is kind of what people are basically shooting for. So fusion, because of those things that were on the previous slide, has the physics opportunity to do this, because it's so scalable and you can't run out of the fuel. You can get there. But can you get there? And the problem is, can we get there fast enough? It's not really about can we get there fast enough? And here's the plan with the idea that we actually have power plants going by the early 2030s. And we are tantalizingly close to this. No, this thing doesn't work, of course. There we go. So fusion sounds very exotic. This is actually one of the reasons why it's so attractive. Is okay. So what do we do? So we basically recreate the conditions inside stars. So we have a device like this one that you're showing here. You can see the person standing beside it that contains a fuel at 100 million degrees. That sounds like the exotic part. We've already got that one figured out. The fuel fuses and releases energy in the form of particles. And much like the sun, basically what you do is you capture these energetic particles and you make heat. And in this case, basically what this looks like then on the outside is it's just an incredibly effective energy generator. It's not an electricity generator, it's a fundamental energy source. So you can turn off and on at any time. This is one of the reasons why it can scale into the present electrical system. But not just electrical system, everything, fuel, industrial processes, everything, because it's an on-demand energy source. So what are the conditions there? So this is interesting because it seems quite exotic. So you have to get things very hot, it turns out. It's 100 million degrees. But the other part of it is that, in fact, the density of the fuel is 100,000 times less dense than air. This is about the intrinsic safety of fusion, is that it's actually, even though it's very hot, there's very few particles. So the energy content of a power plant that would run Cambridge is about that of a pot of boiling water. This is why it's so safe. Actually, it turns out this one, of confining it and putting it, it's kind of like building a fireplace. Confining it for about a second of energy confinement, that's not how long it lasts, it's just how long the energy stays in it to keep it hot. So in the sun, that's about 1 million years. In our case, it has to be about one second. In fact, it's much better than the sun. It has a power density about 10 million times higher than the sun. You don't want the sun to be 10 million times higher. So can we do this science? This sounds like science fiction. Actually, the answer is yes. We've already done most of this science. And these are the conditions which I showed before. 100 million degrees is here on this plot. Here's temperature. And these particularly look at these blue dots of a configuration of what I showed you before, a configuration of magnetic fields. that basically tell us that when you put these two things together, confinement and density of the fuel and the temperature, this uniquely determines the ratio of how much fusion power out you have compared to how much heating power you have to get in to keep it hot. And if this gets significantly greater than 1, then you've got the prospects for a power plant. And you can see that, in fact, the crazy thing that I said, 100 million degrees, have actually achieved in experiments already, including the one here at MIT. What we need to get to is up here, because this is where power plants live. But a few years ago, I would say fusion energy had stagnated and looked distant. So we beat, from 1970, when that particular configuration was invented, to about the mid-1990s, we were beating Moore's law. We increased on, this is a log plot, we had increased about almost 4 to 5 orders of magnitude in being able to obtain that goal. Incredible achievement. And then it got totally flat. Like, what happened? What happened was that it wasn't really a physics limitation, it became a technological limitation. And the thing is that we decided quite rightly to build a device called ITER, which I'll talk about. It became the next step, but it was so large and so expensive, it took basically all the world's governments to build it. It's the largest construction project in the world right now, actually, in the south of France. So I got very frustrated right around here. No students wanted to work on ITER. This looked like it was probably not going to happen while I was still alive. Was there another way? So we basically came up with a new plan to break the fusion conundrum. And the fusion conundrum gets isolated into this, is that the physics of fusion is hard, and we have great confidence in this tokamak configuration. But the problem was, based on known technology, it got enormous. That's a person standing beside it right there, that little person right there. It became very big and slow. At the same time, to give credit, like what usually happens in science and in development, into this vacuum rushed the private sector that said, could there be other ways that we could do it smaller and faster and inexpensive? Yeah, that would be good, and good, let's go try that. The problem is that those are those green points down on the science plot. So it's like you have to extrapolate in science. And great, good luck with that, that's good. Could we come up with something that had high confidence in physics, but that was still fast, small, and inexpensive? It was based on a breakthrough opportunity, which is the fact that a new generation of ways to make energy efficient magnets, which is the key way that we contain the fusion fuel, came about. And this is over on the right-hand plot of this. As an engineer, you start drooling over this. So LTS, low temperature superconductors, compared to this next generation, and basically, I won't go through the details of this, but this essentially lives in an operating space of temperature, magnetic field strength, and how much current it goes through. This was a true break that we didn't develop, but we recognized the opportunity that was there that said, what we have in front of us is a operating volume of this HTS, which is 1,000 times larger than the previous technology. This is when MIT engineers drool, right? It's like, oh, let me go into this space, and others were thinking of it too. But what it meant for fusion, we combined it with our expertise in fusion, is that basically in one fell swoop, if you could actually push this technology to high magnetic fields over the right-hand side of this plot, what this meant was that the linear size, and therefore the investment is going sort of like the cube of this thing on the left-hand, on the vertical axis, that you would be able to dramatically reduce the size of fusion devices based on exactly the same physics of what ITER was based. So what does this look like? So what this looks like is you take a look, so this is magnetic field strength, and on the vertical axis is the linear size of the device. We had already done Alcator CMOD here. It was sitting on Albany Street, just a few hundred yards away from here, in fact. And then instead of going on this route, and then in fact going up to ITER and even making bigger objects than that after actually to make fusion power plants, the idea was to shrink it by factors of 100 to 50. And that's going to make it faster. And that was based on known science. So here they are to scale. And so you can see this is what we had done at MIT. We had proved it. We had reached 100 million degrees. And the idea was that we wanted to build this called SPARC, which would actually show net energy from fusion for the first time. And that would have the same mission as that. So you think, how can that be possible? Well, it comes from the non-linearities in fusion game, which I'm not going to go into. Basically, this was proven science. But the problem was you needed to access the right-hand side of this plot. And that was not possible with the previous generation of superconductors. So what did it look like? So essentially, this new material enabled a new pathway to fusion energy. Fusion energy is possible at economically small scale. And we had done the science, and the idea was in phase 1 of this, we would demonstrate HDS magnets above 20 Tesla. Phase 2, go and build this device, which I just showed you before, called Spark, which would be the Kitty Hawk moment of fusion, which would produce net energy from the first time. And an object that size is producing 130 million watts of power. So you realize fusion's power intensity, and then rapidly go towards commercialization in the early 2030s with an object, again, about this size could power Cambridge. But it took more than this. It also took an organizational innovation, because we had exactly $0 to do this at that point. In fact, I shouldn't say that. I had about a $100,000 gift from a friend of MIT who came in and said, "This looks really promising. Can we get going on this?" And Bill Gates pointed out is that a real energy transformation requires governments, research institutes, businesses, and private investors to work together. So we took that to heart. And in fact, we launched and spun out of the Plasma Science and Fusion Center, which I'm the director, a new company called Commonwealth Fusion Systems that was going to work together with MIT. I'll show this. So we basically said, let's go and find this plan, because it's got an end goal of commercialization. And then it was these people down here that actually came in and supported us. One of the world's largest energy companies, the Engine here at MIT, and these individuals who you might recognize down on the bottom. So this got off to a great start. We announced this just over 3 years ago. And it made a lot of splash in the news in search of clean energy. But it was this twinkle in our eye, confidential between us. And one of the reasons it got off to such a great start was Spark and Commonwealth Fusion Systems were essentially born at scale. We leveraged an existing infrastructure, which was many hundreds of millions of dollars. And in fact, a place, which again is just down the street from here, a whole block that basically had not only facilities, but people that actually knew about how to do this. So off we went, and we built a new organizational model for fusion commercialization with the idea that, unprecedented, we basically, in a Venn diagram, we coupled together a research university center in the PSFC and a private company, Commonwealth Fusion Systems, with a big overlap, which is basically, this was still research, but it was also with a view towards commercialization. So we basically leveraged the heck out of what was at MIT. We got over $200 million of private sector funding. We currently now have about 240 people, about half at MIT, half at the company doing this. We were able to attract both the best from academic and startup worlds. One of our proudest moments was when SpaceX blocked our website because we were taking too many employees from them. We generated 25 patents in 3 years. And we had as rapid tech transfer as you can imagine, because we worked out a novel relationship actually between the company and MIT, that the teams were able to co-develop the technology. So the tech transfer didn't happen in years, it happened in weeks and months. So I'm very happy to report that this was a check mark. This is now a check mark. And there was a little bit of news that surrounded this. In September 5th, we actually achieved, it's still amazing to think about, we achieved 20 Tesla. So this technology actually worked, and the team worked, actually is doing it. So what we are now doing is launching as fast as we can, in fact, into the Kitty Hawk moment and to ARC as well, too. So I'll just so what did this look like? This was about starting at scale. This is the test facility. And as the director, I was able to get MIT to support us to clear out one of the largest experimental spaces at MIT to put in this brand new technological test facility. So this is what it takes to test, by the way, a 20 Tesla magnet. Here's teams, in fact, in this teams that are sitting here is MIT and CFS employees working together, in fact, to carry this out. But this is on the MIT campus, and inside of there is, in fact, the magnet. So that gives you an idea of the scale. It's about so here it is. So we built and tested that high field magnet. Fully representative of Spark and ARC commercial coil operations. And though this doesn't mean much to you, this is basically doubling the magnetic field that was available. It's around 400,000 times Earth's magnetic field, okay, at the surface. Well beyond, basically a quantum leap compared to what the previous technology could do. Here's some numbers. It's at scale. It's like a 10-ton magnet. There's almost 300 kilometers of this superconducting tape inside of it. And it was made out of 16 subcomponents. Each of those 16 subcomponents was already the largest one made ever. So we went fast. We went really fast and was successfully tested September 5th. Very, very exciting. And what does this mean? Well, I'll just summarize the science of this. When you can double the magnetic field, in a superconductor, this is really important to think about. we had already demonstrated high field fusion, 100 million degrees and all this. The problem was the magnet was consuming 200 million watts of electricity when we were running it. We could only run it for 2 seconds because otherwise we'd bring down the Boston grid. That's not a good thing. This magnet made basically the same magnetic field at the same volume and consumed 25 watts. That's why all of a sudden it's a quantum leap towards practical energy systems. And what does this mean? And people knew about this, about superconductors. What does this mean, this quantum leap? So fusion power per unit volume, the most direct indicator of economic, is 16-fold improvement when you double the magnetic field. And what happened in Spark itself, if in Spark we had tried to build Spark with the old technology, the gain would always be less than 1. We leapt over to here, and instantly it goes to 11. So that's how fast you win. And basically at the same time, compared to, as you saw in that diagram, this decreased the volume of the tokamak by a factor of 40 to achieve net energy. So what we're doing is we're going forward with Spark. And there's also another key part of this. Fusion science is still hard. We, unlike almost all the other private sector fusion efforts, and because it was a part of MIT, we went out and peer-reviewed papers, 7 of them about a year ago, that laid out the entirety of the physics of this. Completely bare, because it's not the physics wasn't about the secret. It was not the secret. It wasn't the secret sauce, right? It was really about the magnets. So what does this object do? Makes 145 megawatts of fusion power, takes about 12 megawatts to keep it hot, net energy gain greater than 10. And it's basically that magnet that you saw. We have to build 18 of them, put them into that configuration and get going. The Spark siting is complete. There's what it's going to look like eventually. It's in Devens, Massachusetts, so it's within commuting distance for us and for MIT employees as well too. Basically licensing, permitting processes all going forward, otherwise we wouldn't be doing this. And we have agreement about how to license this and operate it as well too. And literally right now, as I am talking, dirt is being moved in Devens, Massachusetts. There's the thing where the tokamak is going to sit. So this is coming, and it's going to be in Massachusetts, and it's going to have a deep affiliation, of course, to MIT. But the fact that we launched this company is very exciting. And in fact, there's some news coming fairly soon about its next fundraise about achieving this. Another key part is that, and I borrowed this slide from my CFS colleagues, is really CFS is working now with over 500 suppliers. These are vendors, these are industries. There's a whole set of them which are over here, including not just the superconducting tape, but all the things that come around this, cryogenics, power systems, all these kinds of things. And very exciting, CFS now has an active, what an MIT can't do. We can't have a power business unit that's thinking about selling commercial power plants. So this is a part of the power of our relationship, is that we have the R&D and education right alongside, in fact, the commercialization. And it's not just us, by the way. I would also point out there's now almost 30 companies that are started to come out, and some of them quite imitative of us, which I'll take as flattery. But it's actually more than just this. There's a total, when we started this, and really the design of this device, the thing that would be the eventual commercial power plant, all of its aspects were designed in a class that I taught by the people who are now like the C-level executives in the company, and by the way, students who are still continuing to work as scientists at MIT. It's like there needs to be a plan, not just, hey, let's have fun physics. We need to actually get to commercialization as fast as possible. So what does that mean? So there's a comprehensive plan, and everywhere around this, basically the theme is accelerate. So ARC is this high field path, as I said, 200 megawatts electric. We have to close the fuel cycle, establish supply chain, demonstrate operability, regulatory. And where this really means is that in parallel to Spark, I'm not going to go through all the, basically to deliver a real energy system takes more than just the magnets. It takes the holistic view of everything around this, about materials, about maintenance, about fuel, and so forth. And this is one example of a new experiment that is in fact starting right now on the MIT campus to support, in fact, this mission. So the concluding remarks is, the last few months have been sort of mind-boggling to me as a person who's worked in fusion for over 25 years. It's like, how it's crazy how all of a sudden the things just like all come at once. And that's what it's feeling like with the breakthrough. Of course, they say the overnight success built on decades of hard work, right? But this is really telling us something very important. The fusion energy industry thing is not some vague thing that's out in the future. It's here. And it's coming way sooner than previously thought. It's due to breakthrough technologies, and I think the whole innovations, not just in technologies, but around about how we organize and think about going more rapidly towards commercialization. I'll point out there's several famous examples around here about commercialization of genetics and of low orbit space launches. Those things were not thought of as commercial activities. Like, this is coming. It will be highly disruptive. It's probably the most disruptive energy source we've ever made. Because once you get there, you think about it, it's adaptable, it's scalable, although I can't spell scalable, carbon-free, and it's a totally different energy source. It's literally not based on resources. It's based on knowledge. Because the fuel is free. Like, the amount of materials that we actually make to make these things is actually quite small. It's the whole point of fusion. It's why the ultimate energy source. It just scales forever, in fact. And it's no longer just a curiosity-driven science project, but a consideration of how to evolve a new industry with many opportunities for existing industries. Voila, my discussion here. And I would point out is MIT and the PSFC has incubated and launched now a key part of that with Commonwealth Fusion Systems. But what are we going to keep going with? Well, it's the reason that you've got places like MIT and the Plasma Science and Fusion Center. This will be a hub of building the entire fusion energy ecosystem, and I look forward to discussions about that. So thank you.
I mean, are there any questions to it? So really, it's here you have it. There's a freight train or multiple freight trains going to come. It's going to actually really disrupt multiple industries. And, I'm going to start here.
The Q, the efficiency
Yep.
that you mentioned that could achieve 10.
Yep.
What do you expect the ultimate to be?
Oh, right, in a power plant? Yeah. So it's actually not much larger than that. So it depends on the details of it, but some of them are around 15, some of them are at 30. And you go, oh, that's still a factor of 50% or 2 away. It actually isn't like that. It's because of the way that's within, so Spark basically gets within 10 or 15% basically of what you would need in a power plant.
Okay, but this is the plasma efficiency, but then you need energy for the magnet
exactly.
and all of that. So what do you expect?
Yeah.
The efficiency of the entire plant with
Yeah.
all the auxiliaries?
With all the things, yeah. So we have a different name for that. So we call this Q sub E, which means the gain, the electric gain in the system. So right now our electric gain would be probably on the order of 5 or 6, something like that. We actually have other ones and this depends on some of the details of the technology that I have to go too quickly through. So what this depends on is the specifics of how efficient you get the magnets. We think we've got that in hand. Then there's the drivers for putting the energy in as well too. So you got to get, that's probably the key one about the heating power that goes in. But we're pushing towards a solution where that's really quite small. And then in the end, the big one in this is the energy efficiency that you have of converting the heat of fusion into electricity. But this is fairly standard level actually for power plants, yeah. And yeah.
There's another question over here.
First, thank you so much. Your energy is inspiring, I think, for the future. So I wondered, you mentioned industrial processes at the start, and like you just said, it easily transposed into infrastructure for the grid, but can you speak to how it could also easily integrate into industrial processes?
Yes, yeah. So in the end, the units that we're considering, I'll point at one example because this is the most recent example. So the last version of the class that this was generated out of, I always like to ask provocative questions by the way, there's nothing like 15 MIT graduate students to just like launch a problem at, right? I said, this whole business of building electrical plants, well, what if in fact we considered a different market? And the market was maritime fuel. Because like, how are we going to decarbonize like long range shipping? Like, so carrying batteries on a big, those huge all the ones that are lining up off the coast right now because of our supply chain problem. How would you make that green? So we went and talked to some industry experts about that, and they said, well, if you could make generate carbon-free ammonia, that's an interesting prospect, because we can actually, if you know about diesel engines, essentially switch them from to urea, right, to ammonia. So this is what we looked at. And so could we adapt basically the energy product that we were thinking of for electricity into ammonia? And the answer was yes. But this then keeps going. So it really depends on the details of what you want to do. If you want to use this directly as a heat source in industrial and chemical processes, so this really is very important that you get to the right temperature range, for example, of what might be done there. A big one is like, how do you decarbonize like cement and steel production? People forget, like, everyone thinks of decarbonizing as decarbonizing electricity. Stop. That's like 20% of the challenge. It's like, it's fuel, it's industrial processes, it's cement production, it's steel, things like this. It's like, this is highly adaptable to basically almost all of those. It's so great, by the way, giving a talk in front of people again. Oh my gosh, I think I almost forgot what it was like. It's like I'm almost like looking at each of you like you're in your Zoom window.
Thank you. Fantastic talk. So two quick questions. One is around, you said a little bit about these superconducting magnetic tapes, a little bit about what they are and how they operate. And the second one was the question about naval reactors, so submarines, those sorts of things, whether they're appropriate for those kind of applications or too heavy.
Right. So on the what would you like to know about the tapes? So it is an industrial field now. So there are several vendors of this. We bought up a lot of the of the tape that has been produced. In fact, another side note, a very powerful thing of launching a company is that the company figured out novel relationships with the vendors that would not have been possible if we were just MIT to do that. So what's going on now is that there's, what this looks like is very much like what solar panels look like, because it's a thin film deposition process. The scalability of this is that, we have to scale up the production capability, and as that goes up, then the cost per unit we expect to go down. And if you look at that, then that was one of the major expenses of building this magnet, but there's factors of probably 10 at least reduction ahead of us in this. A very familiar story for those who are familiar with these. So it's a scalable process, we think, and there's no exotic material that we're worried about like not getting access to. Well, and the second one was about naval reactors. Yeah, so no, probably. So of course the primary use of that is in submarines. And so it is interesting. One of the limitations of fusion is that it's very, very hard to do at small output power. And it becomes almost impossible actually at small output power. So one of the things, in fact, is how that class started. Everyone thought they would be at least a gigawatt electric. I said that there's no way that's going to happen because that's not going to be commercially viable. We pushed it all the way down to 250 megawatts. But you can't really make it work at around 5 or 10 megawatts electric. And the reason for this is actually on the left-hand side of this. How many working small stars do you see around? It actually comes from the physical process of the fact that it's the fusion power itself that keeps it hot. So at some point you just run out of juice to essentially keep it hot, and it doesn't work. So that's the one place that fusion cannot actually access, which is interesting, which is really ultra small, like megawatt kind of class generation. So it's going to have to be central generators. This is why I'm interested in working more in people who think about such things in the industrial world. Well, if that's the case, and we want fusion to penetrate deep as an energy source, we need to think about, for example, making fuels, because fuels have got a different kind of distribution system than what you've got with, and you can use the existing infrastructure of that. My own personal opinion is we have to figure out how to make carbon-free fuels. It's like we're not going to replace the efficiency of carrying around your energy source in a liquid form. Just way too much infrastructure built up around that. Not any time soon, anyway. So that's why I'm interested in that.
Thank you very much, Professor.
Okay.